Hello, everyone. Welcome to this month's COFFIES Seminar. So this month, the Heliophysics Big Years theme is bonus science. We don't have anything scheduled, especially for this month's theme of NASA Heliophysics Big Year. But I want to mention that last month we did organize a public webinar, which I think we went really well. We got a lot of general audience from the general public, and that recording will be put on our website very soon. And if you missed it for any reason, you can go check on our website to have a look of it. Okay, this month we are very honored to have Professor Sarbani Basu to give this month's seminar. Let me briefly introduce Sarbani. I think most of you have already known her very well, but still, let me introduce her in case for audience online watching the recording that didn't know us very well. Professor Sarbani Basu is the William K. Lemon Jr. Professor of Astronomy at Yale University. She was trained in India and subsequently worked in the UK and Denmark before moving to the US to join the Institute for Advanced Study in Princeton. She later joined Yale in 2000. Professor Basu specialized in study of the sun and other stars using heliosseismology and astroseismology. She studies the structures and dynamics of the sun. One of her most significant early results was determining the sound speed and density profiles of solar interior, which allowed her to claim, long before the particle physics community, that the solar neutrino problem was a problem within the standard model of particle physics, not that of astrophysics. Her current research focuses on the temporal variations of the sun's structure and dynamics, as well as characterizing exoplanet host stars. Professor Basu was awarded the George Ellery Hale Prize of the AAS Solar Physics Division. Additionally, she was elected as Fellow of the American Association for the Advancement of Science and the American Astronomical Society. Let's thank Professor Basu again, and I will hand over to Sarbani for her talk.
Sorry, I seem to have lost my Zoom. Too many windows open. Sorry about that.
No,
thank you, Riju, for the very kind invitation and the kind introduction. What I would like to talk today, and I haven't shared my screen yet, so don't worry if you don't see anything, is basically some new results that I've obtained along with collaborators, one of whom is here, about the solar tachocline. And I would preface by saying I do not understand the results. I do not know what is happening. And I'm hoping that the theorists here will be able to tell us what they think is going on. So that was my big motivation of speaking today. And also it gives me an excuse not to attend a faculty meeting, but that's a different thing. Don't tell anybody. So I'm going to try sharing. Let me see if I can do this. So portion of screen, share. Give me half a second before you see what I really want you to see. Okay. Present to view. Okay, do you see my slide now and just the slide? Good, thank you. So, before I go there, this work was done with a Yale undergrad, Wesley Andrade. It's a long name. It's just the first and the last part of his name. Unfortunately, he decided, fortunately, as far as I'm concerned, he decided he wanted to do computer science. So now he's in the computer science department. He was a bright undergrad who did parts of this work. And this work involved a lot of data that Sylvain provided, and that data was actually instrumental for us to see what we are seeing. So to jump right into the topic, what is the tachocline? Now, I don't think anybody in this audience really needs an introduction, but I thought I might as well start from the very beginning. So this, many of you will recognize, is a contour plot of solar rotation rate as a function. Can you see my cursor? As a function of latitude and depth. The color scale gives you the rotation rate in nanohertz, but I've put in a few sort of translation into days, sort of, not exact. So what has been seen since the first good solar rotation inversion is that the solar differential rotation that we see at the surface tends to continue till roughly the base of the convection zone, which is marked by this dashed line. When it merges, it sort of becomes a solid body type rotation. Now, there is a shear layer here, which I'm going to completely ignore, though it's an extremely interesting layer of the sun, and there's a lot of work which is currently being done on that. I'm going to just focus on this shear layer, the big one, which is the tachocline. Now, these show the same results, but just, cuts at different latitudes. So that's the equator, that's 30 degrees, that's 75 degrees. And the reason for showing it this way is that you can see the transition from the fact that different latitudes have different rates in the convection zone to somewhere near the base of the convection zone. They all change and merge into what looks essentially like a solid body type rotation. In case you're wondering, the solid lines are the results and the dashed lines are the uncertainties. So even though this looks like a hodgepodge, they're really within errors. It's a solid body rotation. So the tachocline is basically this layer here. Now, this is by no means the first time anybody is studying the tachocline. I mean, Sasha Kosovichev, who I think I saw among the audience, first tried to characterize where the shift occurs in 1996 using the then available data, which wasn't much. And then I tried something similar the next year, and there has been some work, I think a couple of papers every decade since then. Now, if we look at what the tachocline looks like at different latitudes and depths, this is a schematic based on some results that I had with a collaboration with Antia in 2011. That was the first time we tried to find time variations. So that's the equator, that's 60 degrees, and you can see that at the equator, the change seems to occur. These are results of fits, by the way. Change occurs below the base of the convection zone, which is shown by this gray line, while at higher latitude, it occurs at slightly shallower layers. And this result showed that the tachocline seemed to be prolate. Now, in 2011, we had, about a solar cycle worth of data. By the time I looked at it again, just to look at the time variation, we could actually see a time variation, but only in this quantity that I call the jump. That is the change of the rotation rate between the equator and the deep interior. And what we found in 2019 was that the jump was not at the same value of solar activity, in this case quantified by the 10.7 centimeter flux. At the same value of the activity, the jump at different latitudes was different during cycle 23, which is shown by the red and brown points, and cycle 24, which is shown by the blue and purple points. Okay. So clearly, even though there is a time difference, there's a time variation, it's not a very simple function of solar activity. And at a given cycle, you can actually see a sort of hysteresis-like curve. Now, people have seen this hysteresis-like curves in the changes of solar frequencies before. So that itself didn't surprise us. But what did surprise us is that at the same value of the 10.7 centimeter flux, cycle 23 and 24 behaved differently. And when I had updated these results in 2022 to give a talk with some points for cycle 25, and cycle 25 seemed to follow cycle 24 at that point. Now, we saw these changes in the jump across the tachocline, that is the transition in the rotation rate. But with these data, we couldn't see any statistically significant change in either the position of the tachocline, that is the midpoint of the transition, or the width, meaning the distance over which the transition occurs. Now, to give you a bit more background, this particular figure was obtained with results from 108 days of gong data, but in the same paper, we've analyzed the usual 72-day MDI and HMI data. Okay. So with the 72 data, or even the 108-day data, we couldn't really see a time variation in the position and the width. And the problem was that the uncertainty, it was noisy. And this is where Sylvain comes in, because Sylvain very kindly obtained frequency splittings, which is used to get the tachocline. After all, we're dealing with rotation, for different lengths of the time series. He has the usual 72-day, which is not shown in this figure. He has roughly 1 year of data, which is 5 times 72, which is almost a year. He has about 1.5 years. I apologize, this is a figure from an older paper. Now we actually have 2 years of data, that is 10 times 72-day data. And I think this data is crucial because the longer sets, the 3-year, which is 16 times 72, and the 6-year data, they sort of, you can imagine if you have a time variation, you have a long time series, you're going to basically get rid of all the variation. Now, the previous work here, what we did was we actually used all splitting coefficients from, A1 to A7 and try to do a 2D fit. And the problem is that A1 is very well defined, A3 is well defined, but A5 and A7 have larger errors, as we can see in this data set. So what's shown here is the lower turning point of modes on the x-axis. The y-axis is the splitting coefficient. These are the splitting coefficients in the Ritzwaller and Lively basis functions. So if you want to get Jesper's normalization from here, you have to multiply it by factors, but that's just a normalization. You can see that A1 or C1 seems to have a small Tachocline signature here, but it's tiny. And even here, the uncertainty is sort of masked. A7 and A5, or C7 and C5 in this figure, also, you can't really see. Incidentally, the red points are basically averages of 50 points, roughly. And A3 or C3 is the one with the largest signature. So I decided to go back to what we had done in 1996 and 1997. Sasha Kosovichev in 1996 just used this coefficient A3, and I used the same thing in 1997. At that time, we were just trying to characterize the tachocline. Okay. Now, given that C3, the signature is the largest, and the relative errors on the splittings are, pretty small. They're not small, but pretty small. This, by the way, is, I think, a 3-year data set from a 3-year data set. What we decided to do is look only again at this, okay, to see if we can see any time variation. Now, just to go back to basics, I should remind people of what once upon a time was known as 1.5D inversions. Basically, you could invert the different coefficients which were related to different components. You could actually decompose the rotation velocity in terms of the derivative. The var theta here is the colatitude of the wire lengths. And so you could, if you could find, so each coefficient only has a radial difference, okay? It has a radial dependence. The latitudinal dependence comes through the wire lengths. So if I find the radial dependence of the rotation of, say, C3, I can then find the latitudinal dependence, given our, this derivative here. So all I care about is I'm going to care about is C3. I don't care about anything else, at least in this work. So how did I characterize the shape of the tachocline? And I've again gone back to basics in the sense I go back to my 1997 paper, where I had modeled the tachocline in 1D, in just radius for C3, as basically a sigmoid function. So delta omega is what I had called the jump, which is the change in the rotation rate between the convection zone and the interior. RD is the position, which is the midpoint, the radial position of the midpoint of the jump. And the width in this definition is twice the width is where the rotation rate changes from 0.269 to 0.731 of the jump. Now, this is not the definition that people like Sasha or Paul Charbonneau had used in their work. They had used an error function. But if the width is small, then the two functions look roughly the same, as you can see as I show here, as long as the W for the error function is set to 5 times the W for the sigmoid function. So I stuck to the sigmoid for 2 reasons. One, this is what I had done forever. And 2, it turned out to be easier to fit. But that was a different reason. So what do? We take this model, we calculate the C3 coefficients, and then compare the coefficients. So we are doing a forward modeling. So given this model, rather this model, how do the splittings look like? So this is basically the C3 splittings, okay, for 2 sets of jumps, 2 different jumps, same position and width. One is at minus 19.5 and one at minus 20.5. Does it look anything like the observations? Well, just to remind you, this is what C3 of the observations look like. And it shows the minus 20.5 value because it's close enough to what we see here. Okay. So you can see all that the change in the jump does is displace these curves, which makes the jump the most well-determined parameter, which is why even with shorter data sets, we could find the parameter very, very easily. The effect of the width and changes of the width and change of position are more subtle. So here I have changes of the width, but the width change is, remember, in the 3rd decimal place. And the reason I chose that is that's the sort of order of magnitude we're talking about. So you can see why determining a time variation of the width would be difficult. The signature is much more subtle. This is change of the position, I beg your pardon, and this is the change of width. So the signatures are subtle, and the difference in what happens if you have a different position is you displace the curves slightly along the x-axis. If you have a difference in width at the same position, the curves intersect and cross each other. But since the effect is small, it's difficult to disentangle. So we tried two ways of getting the results. The first was a grid-based modeling, where I used what people normally do in astroseismology, make a huge grid of models, calculate their whatever observable. In this case, it's the splitting, which is easy enough to do, and compare with observations in a sort of likelihood manner. And the other was an optimization through a simulated annealing technique. The second one is something I had done before. The first one is something we decided to try out with the undergrad who was working with me, so with Wesley. Okay. So in the first case, basically, we made a grid of 15,000 models covering the 3-parameter model space. And this was, the models were basically a 3-dimensional Sobol sequence. And for those of you who are into grid making and you have to deal with multiple parameters, you would know that a Sobol sequence covers the parameter space uniformly much more rapidly than a truly random sequence would do, which is why we visit this. Then what we do, we find the chi-squared, total chi-squared between the observables of the grid and the data, calculate the likelihood, and based on one of the more used astroseismic data sets, what we do is we assume that the parameters of the Tachocline, in astroseismology, we do the parameters of the star, are basically the average of all the parameters for which the likelihood is about 0.9 of the maximum likelihood. It's greater than 0.9 of that. You can change this. It doesn't change the results too much. So when we did a comparison of the grid results obtained by the grid-based method to simulated annealing, that is when we decided to stick to simulated annealing. So what I'm showing here are the parameters of the Tachocline obtained for a set of models with known parameters. So I make a set of test models, add errors to the splittings, and then try to find the parameters. Now I know what the parameters I should get back. So this on the y-axis is you could say, the error in the parameter. That is what I obtain minus the true error. Okay, so this is the error for the jump, error for the position, error for the width. This is the grid-based method. This is the simulated annealing. And you can see for the grid-based method, we do fine for the jump and the position. For these two parameters, both methods give equivalent results, and I'll show you very soon an observed set. But for the width, the grid-based method gives a width-dependent systematic error, which, of course, since we want to look at, there is a bit of that even in the simulated annealing, but this is so large that we decided to drop this, because after all, we want to look at changes in the width too. So this is a comparison of the grid-based results for the set of 2-year data as a function of time. This is the jump, this is the position. Red is simulated annealing, cross is grid, and you can see we get very consistent results with both, even though the philosophy of the two fitting methods is quite different. But because the width error for the grid-based was dependent on width, we decided that we will show only results for the simulated annealing. And so going forward, that's all I want to show. So first thing is, can we fit the data with simulated annealing? Well, of course, I wouldn't be talking otherwise. So this is one of the fits. The cyan background are the data. The red points are the model that we fit. So you can see, yeah, it's fine. We do fit the data. The chi-squared per degree of freedom here is about 1.3, I think. I don't completely remember, but it's a perfectly respectable fit. So yes, the sigmoid function does work, but then we had chosen it knowing that the C3 coefficient looked something like a sigmoid function. Okay, So coming to results, what do we see? So I'll start with the 1 year results. That is the results obtained by the 1 year data set, because for the 1 year data sets, we have data that have been, the time series have been fitted by Sylvain Kozenik, but also from the official MDI and HMI pipelines. So here it is. I know this graph is very busy. Let me just walk you through this. Each row is one of the parameters. So on top is the jump, middle is the position of the Tachocline, bottom is the width. We are plotting these as a function of time, okay? You might just be able to discern the sunspot number marked in gray in the background, just so to give you an idea of what phase of the solar cycle we're talking about. The solid vertical lines are the sunspot maxima, and the dashed lines are the sunspot minima. Now, let's look at the jump. This lower curve are the results obtained with Sylvain's fit to the data. The upper curve are from the official fit. So yes, there is a systematic difference. Actually, there's a systematic difference between the overlapping MDI and HMI data too. But since all I care about is the time variation, and the time variation in both of them looks the same, I'm not too worried about this. Yes, at some point we have to dig deep and figure out what the differences are caused by, but at least as far as the time variation is concerned, we're getting the same thing. There is, coming to the position, you can see that even with 1 year data, we are beginning to see hints of change with time. Particularly cycle 24, definitely there seems to be something here. But again, there's a systematic difference between the official and Sylvain's pipeline. But okay, both of them still show the time variation. So we're fine, I think, at least I would claim. Width, you can see the uncertainties are large enough that from this particular figure, I don't think you'd be willing to say there's a change in width. So even 1 year data are not good enough if you want to look at changes in the width, which is unfortunate because you do want good time resolution. So next, I'm going to come to what do we get with longer data sets. First, I'll quickly go through the jump. Well, jump, we know this is 1.5 year data. Well, yeah, jump was anyway clear. You can barely see the error bars here. 1.5 year, 2 year, 3 year, 6 year. You can see that as you decrease the time resolution, the curve becomes smoother and smoother. You expect that, so that's okay. But note again, this is what I had shown in one of my first slides with old results. Cycle 23 and cycle 24 don't look anything like each other. Yeah. So now let's come to things which we hadn't seen before, at least not the time variation, the position of the Tachocline. Okay, so starting again, 1.5 years, 6 years. Now you can begin to see that there indeed was a change. Okay. Now there's 2 features which are there in the data, which I don't know what's happening. There seems to be a sudden change. Now, with Gong, I think that is when Gong Classic changed to Gong Plus. So had I seen this, oh, by the way, I should have said again, black is Gong, purple is MDI, pink is HMI. Okay. Now, if I had seen this jump only in the Gong data, I would have said maybe it has something to do with the changeover from Gong to Gong from Gong Classic to Gong Plus, but you're also seeing it in MDI. Okay, so it's not really just it's not a data set issue. Is it a fitting issue? Well, you see hints of it even in the official 1-year data. So it's unlikely that it's something introduced by Sylvain in his pipeline. You see it in the official pipeline too. So we do not understand, looks real enough, what happened during the maximum of solar cycle 23. That's the maximum of solar cycle 23. Okay, what happened then? What about the width? Okay, again, it seems. So the reason I like this 2-year data, you can see that it's a nice compromise between being able to see time variations and the uncertainties in the data. You can see again, if you just look at the width, that the changes in cycle 23 and cycle 24, they're very different. The one thing that occurred to me when I was writing this paper is that we've never really looked at these data, taking both the position and the width into account simultaneously, meaning the overall sort of extent of the tachocline. So what we plotted was R, which is the position, RD, which is the position, plus or minus WD. Now, isn't this interesting? It appears that there are these narrowing and widening and narrowing of the tachocline. Now, just to orient you again, what I'm plotting is basically this part, which is R plus W, that's R plus W, and this part, which is R minus W, okay? I could have, stuck to the error function definition, in which case this would have appeared bigger on scale, but it's basically the same thing. So to me, this looks, I don't know what this means, which is why I'm looking to the theorists. It seems that a tachocline comes closer to the, so by the way, this is the gray line is the base of the convection zone. You closer to the base, you become thicker, come down, go back, come down, go back, come down. I said too many go back, come downs. We don't have too much data on cycle 25 yet to see if that happens. So these were the data that we obtained. And the question is going to be, what's going to happen here when we get cycle 25 data? Now, this is where I'm going to beg your indulgence and going to do some speculate a bit. Now, if I look at the jump, okay, I can see jump even in 72-day data, and that is the jump in 72-day data. These are just Sylvain's results. So black is gong, again, purple is MDI, HMI. Now, because it's 72-day data, we have a better time resolution, but more than that, because it's 72-day data, when we did the work, we had more data sets on cycle 25. So when I looked at this, I felt that the cycle 25 was sort of mirroring, the rising part of cycle 25 is mirroring the falling part of cycle 24. Okay. To show it in a bit of close-up, this is cycle 24, cycle 25. Now, if you look at sunspot numbers, this dashed line marks the minimum. But I found that if I took a date which is slightly before the sunspot minimum, this results look, what I'm about to do is going to look prettier. But I sort of said, okay, 72-day, the sunspot numbers are averaged. It's a running mean over many days, while here we are taking data over a slightly different period, so maybe that's it. So this to me looked like this is a mirror image of that. So what I did was quite literally I mirror reversed this set of points around this line and this set of points around this line to get the cyan points here. So yeah, they look the same with an uncertainties. So my question is, if we get cycle 25 data, will the cycle 25 data mirror image, the falling part of cycle 25, be a mirror image of the falling part of cycle 24, meaning this will go down here because this was down here, and will cycle 26 be a mirror image of cycle 23? Now, I'm basing this on just a few years of data, but it's just fun to speculate because that would mean, for one thing, there's a much larger cycle going on in the tachocline, not a longer cycle rather, going on in the tachocline, at least when it comes to the jump. I have no idea why or what. I mean, for that matter, why is the jump changing? It might also explain why cycle 23 and 24 look different at the same level of the surface solar activity. But as I said, I don't know what are the physical processes going on? Okay. So what next? Okay. We need to keep gathering data because 2.5 solar cycles of helioseismic data is really not enough to study processes which have, at least on the surface, have a time, a period of 11 years. I mean, if you use 2.5 cycles of data in any physics experiments, they would say, oh, you're barely resolving things. So and particularly we need to keep monitoring, because do we really indeed have longer cycles as you go deeper inside the sun? An aside to the HMI team here, hey Charles, I know you were there. Does the official pipeline have a bandwidth to produce 2-year data? Because that's what actually is giving a nice compromise between uncertainties and time resolution. I know 2-year data can be produced because Tim Larson had produced a 2-year set for me for the minimum between cycles 23 and 24, but it's not a normal data product, but it would be lovely to have it. The other thing we need is it's something I'm thinking of very carefully, is how can we leverage new methods of data, of model fitting to get more precise properties of the tachocline. But that's just getting the properties. I mean, we can already see that the jump is changing in a weird way. So we know at least the jump changes in a funny way. So what we really need to do is try and understand what this means. What is it doing? Okay. What causes this change? Now, I remember in one of my previous papers, the referee said, this may just be the torsional oscillation going deep inside the convection zone. Yes, the torsional oscillation does seem to go up to the base of the convection zone, but if it were the torsional oscillation going to the base of the convection zone, why would the width change? I would expect the jump to change, but not the position or the width. So I don't think it is the torsional oscillation, but I don't mind being proved wrong. So I would like to end here. I see there are lots of comments in the chat, but of course I haven't been able to monitor the chat. I'm happy to answer questions now. That's the end of my formal presentation. Thank you very much.
Okay, great. There are already a lot of discussions in the chat. So and also I see a hand raised by Lauren.
Lauren,
So
yep.
Yeah, so Lauren, you can ask, and then if you encourage in the chat any unanswered questions, please raise your hand. I'll ask Lauren to do first.
Okay, great. Thank you very much. That was really, really a fascinating talk. I was wondering for the jump well, first I have a clarifying question and then maybe a real question. For the jump is the changes in the jump, can you tell if that's caused by the convection zone rotation rate or the radiative zone? In this, like, could there be an oscillation in the overall solid body rate of the radiative?
That is an interesting question, and I do not know the answer because most of my work on rotation changes has been sort of confined to the torsal oscillation, and for that, as you know, that we basically look at just the convection zone. But that's a very good question, and I will make a note about it, because all we need to do is look at, for example, look for the changes. I mean, I can just go down and look at the changes there. It shouldn't be difficult. I mean, of course, the uncertainties may be large, but I think it's doable.
Okay, great, thank you. Let me let other people go.
Though I am inclined to think it may be changes in the convection zone, but I'd rather not speculate there. I don't really know.
Okay, sounds good. I'll hold on. I have many other questions.
Okay, so I think Sasha.
Thank you very much.
Yeah, thank you. Sasha?
Oh, hi, Sarbani. Thanks for the interesting presentation. I have a question. How you actually account for the surface changes? Because, you know, this forward model includes surface changes.
Yeah.
And in fact, we can see similar behavior as you jump just in a coefficient A3 or C3 if you plot just function of time. And we actually notice this unusual behavior of also for F mode. So it's not just a property of Tachocline.
Yeah, so the answer is we only use modes. That's one of the reasons I showed you the figures as a function of the lower turning point, which have a fairly narrow range of the lower turning point. I have done experiments to see if, you know, by changing by model to include a near surface shear layer, whether that would change the results that I get for that small region of the radius. And those are all well within uncertainties, and it doesn't seem to affect the results. So that's the one nice thing about using C3. If I use C5 and C7, I would have to, or I did a full 2D fit. In fact, I'm currently trying to do a full 2D fit to examine the shape of the tachocline. That's going to be maybe a talk 6 months from now. There you have to be careful about, you know, changes in the near surface shear layer and be able to model all the changes throughout the convection zone.
Yes, but my comment is that not just modes that that have turning points in Tachocline shows behavior, but also all modes for this coefficient shows the same behavior. If you plot just mean, I think it's published in our paper with Krishnandu. If you just plot the function of time, C3 or A3, it shows similar behavior, kind of longer time variations, not solar cycle.
Yeah, no, that is true.
So it's not a property of Tachocline.
No, it isn't. No, you're right. It's not just a property of the Tachocline. In fact, in my 2019 paper with Antia, we had a figure of showing changes of A1, A3, A5, and A7. But we were showing that for the near surface shear layer, and none of them looked like the solar cycle. A1 looked like the solar cycle, sorry. A1 was closest to the solar cycle, but none of the others do. But the reason I'm a bit surprised is mainly that's preconceptions, right? I mean, modern flux transport dynamo theories aside, everybody thinks, okay, most of the magnetic fields are generated in the tachocline and we have an 11-year cycle, so why aren't we seeing an 11-year cycle? So, yeah.
Yes, dynamo models don't explain this, yeah, we know
Yeah,
this.
I know. So,
Okay.
yes. No, you're
Yeah.
right. We see it also close to the surface. And my 2019 paper, it's either figure 1 or figure 2 of the paper, we showed that.
Okay, thank you.
Nick?
Hi, Sarbani. Thanks. This was very stimulating. I need to stare at a lot more, but I just wonder, the only thing that bothers me is cycle 24 was kind of an anomalously weak one. I wonder if we're getting screwed, just not looking at a particularly good cycle 24.
Yeah, but cycle 25 is getting stronger. So I think cycle 25 will answer your question.
Yes, I agree. I'm hoping. I mean,
But the thing is, let's see if I can go back to one of the older slides easily. Oh, yeah, I can. My older jump results. Come on, here, this one. Cycle 25 seems to be following cycle 24. These cyan points here are cycle 25. They seem to be following cycle 24.
yeah, right. But it looks like it hit rock bottom and it's coming back up.
It's coming back up. So the question is going to be, what is the falling phase of cycle 25 going to do? And it's that which is why I called it speculation, whether it's going to keep mirroring cycle 24 or do something different.
Right. Yeah, I'm with you. I'll wait with bated breath.
Yes, I know. And I wish, as a person who studies solar cycle, I wish the solar cycle was shorter.
Yeah.
Bunny, you need to be patient. But Nick,
Yeah, but the thing is,
see,
I started doing helioseismology in 1993. Okay, good data started coming in 95. So an average astronomer's career is what, 3 solar cycles, perhaps? 3.5
above
solar
average, Sarbani, we
cycles?
expect more. But Nick, to just come back for a second, the two different, mode fittings still show us the same thing. So
Yes,
even if you say
precisely.
that cycle 24 was unusual, we still have to explain why the sun decided to throw an unusual cycle 24 and not hope that all the other cycle will be matching your expectation. Nick, that's my
No, but the thing with the
conceptual
unusual,
comment on that. Sorry, Sarbani.
Yeah, sorry, didn't mean to speak over you. Zoom has an, time lag issue. The thing about cycle 24 being unusual is we say that that's where we have lots of data. Look at the solar minimum in the early part of the 1900s. There was this, I think it is the minimum between around 1910, where solar eclipse images during the minimum looked like the solar corona during the 23 and 24 minimum. And if you remember, the corona during the 23 and 24 minimum did not look like a normal solar minimum corona. And photographic images from way back then seem to show that. So it's unusual because we haven't seen it. And we only have data for helioseismic data for, not long. Because unfortunately, Bison data, which goes down a little to cycle 21, that's only sun as a star observation, so that won't show anything like this. Yeah. So Sean.
Yeah, how similar are the mode sets from the different fittings?
They are quite similar, and to do this work, all of Sylvain's sets are used exactly the same data set for all of them, meaning the same N and L values.
Okay.
I did the same for the official pipelines. The official pipelines is a bit more varied, but since I was going to use the longer data sets anyway to get most of my results, so no, it's not a mode set problem.
Yeah, okay. But do you understand the difference between the Sylvains and the pipeline?
No, I said that. I don't understand that. In
Okay.
fact, there's a difference between MDI and HMI pipeline. Look at this guy out here.
Yeah.
I don't know if Charles knows what that is about, but maybe Tim Larson knows by now. I don't know. Tim and Jesper? I have no idea.
No is the answer to your question.
Okay, yeah, I thought so.
And of course, Sylvain has a totally unbiased opinion on this.
Kieran?
Yeah, actually, can you go to the previous figure where you were showing C1, C3, C5 variation at different latitude?
Yeah, I am pretty sure I can show that. I showed it just for one data set. Here. Oops, no, this one.
No, other one, where you were showing hysteresis.
Oh, the old figure from the
Yes.
2019
So,
paper. Yeah.
yes, so I can see this, you are getting hysteresis at equator and 60 degree, not at
Well,
other latitudes.
the thing here is, Kiran, these were from a 2D model.
Mm-hmm.
So the other latitudes, I mean, what you're seeing here is actually redundant information. It's only factors of cosine squared and cosine to the fourth colatitude that is different. So it's that factor which makes it look different.
Okay,
Yeah,
that makes
so
sense.
so I wouldn't interpret it, but equator is the one I would believe, because cosine squared colatitude is 0, so nothing going on there.
But for 15 and 45 degree
It's
behavior is
because,
very
again,
different.
colatitude.
Yeah.
So,
Okay, then. Thank you.
yeah, though, yeah, I should plot this for Sylvain's data to see what happens. But these were 108-day data, so maybe I should plot the 1-year data. That should be good enough. See what
Yeah,
happens.
that will be really good to see what
Yeah.
kind of behavior you get.
I just haven't done it. So.
Yeah, okay. Thank you.
Sylvain.
Comments. One, I want to remind, and Sarbani correct me, that this new work with my data is a 1D, analysis versus previous work that was 2D.
Yes.
You will extend that to 2D, so people have
Yep.
to realize that currently this is just a focus on the equator. There was a question earlier, and I tried to answer, but maybe you have a definite answer. Have you done the same work when you use the symmetric and asymmetric fits? Am I correct to say that there is almost no difference?
Oh, I should show you. It was in the figure. I just didn't point it out.
I know, but somebody asked about it because there is
Yeah.
always the same
Okay. Yeah. Okay, hold on.
argumentation about,
Yeah. Okay.
getting symmetric, asymmetric.
So this column is symmetric. These are 1-year data. This column is symmetric, and this column is asymmetric. And the reason I showed symmetric and asymmetric only for 1-year data is because both Sylvain and the official pipeline have symmetric and asymmetric fits, though for different coverages. Like, for some reason, Tim had a lot of asymmetric fits for, HMI, but not as many for MDI. Just to remind folks, the default MDI and HMI frequencies are the symmetric ones. There are a few, at least people use default symmetric ones for those. So, but given that there was both, this is what we get. The jump looks exactly the same to me. There may be slight differences in the position, or rather the change in the positions, but I'm not sure. The uncertainties are large enough.
Well, Sarbani, if you remember, the asymmetry is not a function of M, so
yeah, true.
Ignoring the
function of frequency,
which
yeah,
is the way I want to set it up.
Yeah.
I want to say it because we know the modes are symmetric.
Yeah.
It's just shifting, the measurement of all the modes. Because
Yeah.
if it's the same asymmetry for all the M's, you're essentially making a systematic similar error for all the M values to first order. So you expect only second order, minute differences.
And these are small enough differences that they're difficult to tease out anyway. So I haven't looked at the chat at all because it's oh, there's so much in the chat going on. Sorry.
But by the way, if you look carefully in the middle row on the right, you can see that the blue points are less offset when you look at asymmetric versus symmetric.
Yes.
So the asymmetric value give a more consistent estimate
Mhm.
of the position of the discontinuity of the Tachocline RD,
Mhm.
which is what I would have expected
Mhm.
if you indeed recognize that the modes are symmetric.
So Shay has made a comment about meridional circulation, etc. Now, Sasha, wasn't one of your hypotheses about why should there be a change in the Tachocline something to do with you and Douglas Goff had a preceding paper? So that the meridional circulation could change things?
Yes, we discussed shape of Tachocline.
Yeah.
But Sarbani, I have a question about the structure of Tachocline from your inversions. Can you show your inversion results that you showed at the beginning?
Okay. Yeah.
That's a question that puzzled me for many years, and I don't know the answer. But your
Okay,
data
hold on.
seems to show that it may be the real effect. No, when you have inversions,
Oh.
rotations, that you probably second slide or so.
Yeah. Okay. This one. This one?
The next one, yeah, next one.
Oh, the.
Yeah, here you can see that what Tachocline is a decrease of angular velocity, but then you can see it below the Tachocline, what we call some bump here.
Yeah.
And it always appears in inversion results and in all data that I've seen. And we can see this artifact, maybe the side lobe, but it doesn't look like side lobe.
It could be because these are RLS inversions, so there could be a side lobe. On the other hand, like if you look at how the uncertainties increase, I mean, yeah, at 30 degrees, the uncertainties are tiny, but at 30 degrees, things are really flat. So yeah, it would be interesting to, now that we have the longer data sets. I think that the 3-year data, inverting the 3-year data sets might actually show something what's going on if there are indeed differences.
But actually your C3 coefficient indicates that it may be real. You can see if you look at, if you plot your gain with blue and red dots in A3, you can see kind of decrease, you can see the last point. At 0.6, it shows some variation down, so it's indication that this variation
Could be.
below 0.7 may be real.
Yeah.
Because this
And
curve should go up
similarly,
in your theory. That, yeah.
And similarly, C7 seems to, but yeah.
Yeah, that's something.
Sylvain, you have been doing inversions, I believe,
So
with the longer data sets.
So if I can make some comments, and
Yeah.
this is not in any way, detracting Sarbani's work. Let me make it very clear. I think that we really need to focus, one, on seeing whether we can improve the fitting and get even more accurate data on what we have. This is something I've been repeating for probably at least the last 10 years. The other thing is that we need to improve our inversions and try to really see whether a full 2D inversion of the splittings, not the expansion coefficient, can give us a better handle on the Tachocline. This is what I've been focused on. And when I invert very long time series, I don't see this little bump. It is incredibly sharp and then absolutely flat below the convection zone. I need to still do some more testing and make sure that, I've tuned my inversions the way I like it. This is work in progress, but, I think that one of the answer is pushing there and improving remote fitting. And that comes back to even what, Tim has found, that even our gap filling can be improved. I always say, I'm going to have a square root of 2 in 25 years. And, I'll be not as sharp as I am today in 25 years, but we can try to get a square root of 2 improvement on the precision if we rethink very carefully how we do the whole global heliosysmology pipeline, if you want to have answer to all those questions.
Yeah, the problem, of course, with a very long data set is that your mode parameters themselves could become uncertain, because I would imagine the solar cycle shift in frequencies would make your peaks appear wider. If you take,
I agree, Sarbani, but the point is that on very long time series, we can try to see how well we can improve the methodology, and then see whether the better methodology can give us better precision on shorter time
On the
series.
shorter time, yes, indeed.
My whole methodology was initially developed using a long, time series. And if I have a much longer time series, I can try to fit more parameters to do a more, complicated, for lack of a better word, or more, involved fitting. Maybe we can let the asymmetry not, to be a function of M and things like that. But you need to have a very, robust methodology, because once you add too many parameters, you have issues of stability in your fitting.
Actually, if I come back to the question of whether the jump is the change in the rotation rate, difference in jump is because of change of the rotation rate in the convection zone of the deep interior, if I just take model splittings for the same model but just change the jump, this is where things change. Of course, it's changing here too, the splitting. So it comes back to, I don't know, is this the clearest signature of the jump? Or, I mean, can I find the jump just by taking the average of the splittings here? And I think we can. But yeah, I haven't tried it out. I should have let the undergrad do that. That's the sort of things they're good at. But didn't think of it that time. But that's why a discussion like this is so useful. Is there anything else?
It seems we addressed most of the questions in the chats, and I wonder for the people in attendee, since you don't have access to chats and things, or maybe not raising hands as well, but if you have questions, please just speak out directly. If none, if no more questions, we can close the hour. We are a few minutes over the hour, but we started late as well. So thanks to Sarbani again, a wonderful seminar, and I really enjoyed a lot of discussions afterwards. So if there are for future questions and collaborations, please attend our COFFIES meetings. So okay, so see you. Well, next month is AGU week for the seminar time, so probably see you at next seminar in January 25. Okay. Bye.
Bye.
Bye-bye.
Okay, bye.